Hello everyone, we are back to our tutorial class. So this is tutorial 6 and in this we will be studying plasma devices, characteristics and investigate some plasma parameters that may occur in different types of plasma, and that part will be very interesting. Now of course the plasma devices and characteristics, I will just summarize what we have learned in our regular classes. So thermal plasma devices, they operate at high temperatures. This very high, whatever is written there, is compared to a regular experience. This is not with respect to the fusion kind of plasma, where you get millions of degree Kelvin. So compared to our daily experience, where we are used to have temperature around less than 100, so compared to that, this 5000 to 20,000 degree Kelvin is really high, and at this temperature, uh, any material will just not get evaporate, it will become plasma. Okay, they will get ionized as well. So these plasma devices, thermal plasma devices, are operating in this range 5000 to 20,000 degree Kelvin, and there what we will do, actually we will try to understand the kind of ionization that is happening there, and this collision is significant, so that the electron temperature and heavy species temperature, they mostly equilibrate and you get a plasma where all the particles are thermalized, that is they are all having the same temperature, but this temperature is different from the radiation temperature. So radiation equilibrium is not there. Now usually we generate the thermal plasma using radio frequency discharges or arc plasma devices. Um, some of the applications are plasma torches, DC, RF devices, and arc welding, cutting, then plasma reactors for material processing, where we are directly using the arc to melt materials, all these things. So these are some of the applications. We have elaborated that well in our regular classes. I just want to make you remember that these things are there. Now these devices operates with two kinds of electrodes. One is thermonic cathodes, and another is the thermochemical cathodes. So thermonic cathodes, which are they emit electrons via thermal energy, that is tungsten. Tungsten basically emits when um, you are using 2% thoriated tungsten. This is the commercially available tungsten cathodes which are used in these devices. If you do not thoriate it, I mean if you do not include the oxide, that is 2% thoriated tungsten, 2% thorium oxide impurity inside that, then the pure tungsten is having a work function which is more than 4 electron volt, and when you thoriate it becomes less than 3 electron volt. So that is the benefit you get. So most of the time we are using thoriated tungsten as the thermonic cathodes for inert gases, but for reactive environment this tungsten cathode uh, will not work, because tungsten become tungsten oxide that time. If you are putting say oxidative environment, then tungsten oxide is having a melting point only 1400, whereas your pure tungsten is having a melting point of more than 3000 degree Kelvin. So that is why these electrodes 2% thoriated tungsten cannot be used in case of oxidative environment. Now for thermochemical cathodes are those which use chemical reactions at high temperature to enhance electron emissions. Okay. Now one of the thermochemical cathode is hafnium. This hafnium becomes hafnium oxide when it gets in touch with oxygen, and hafnium oxide is having much thermal and electrical behavior, much better thermal and electrical behavior compared to pure hafnium metals. So that property um, arises when it undergoes chemical reaction at very high temperature of the arc as it operates, and that allows it to operate in a much better manner compared to what um, is available with pure metal like hafnium. And in this case, actually, unlike here, the melting point of tungsten that reduces by say 2000 degree centigrade, in case of thermochemical cathode, the melting point increases instead of decreasing. So that is another interesting behavior which makes them to stand in such active chemical environment at very high temperature. So the key difference is that thermionic emission depends solely on temperature, and thermochemical cathodes involve catalytic surface reactions while emitting. So these are the thermochemical and thermionic cathodes which are basically being used in the area of thermoplasma devices, and most of the devices can be made using these two type of cathodes. Now, what are the features of the electrodes? They must be able to withstand high thermal and electrical loads. Of course, they have to, because you are dealing with very high temperature, as we have initiated started at the beginning, that the temperature is 20,000 degree Kelvin or around that. It may happen, it may occur in such in operation of such devices. And electrical loads, of course, these devices usually carry very high current. For example, the arc devices can go up to 1 mega ampere, okay, in certain cases, and a few hundreds of amperes are very common in arc plasma devices. Now, they must be made of refractory material, that is having very high melting points. So that is why actually when you are operating with inert gases, tungsten may be the best material that you can have for operation of these devices as cathode. Actually, tungsten is used as cathode, and they must have good thermal conductivity that is required, because the amount of heat that is getting dumped over the electrodes, they must be carried away by the coolant that you are passing through these electrodes. Now, for taking away the heat, you must have good thermal conductivity of the material. If it is not there, then the heat will accumulate in the bulk of the material and it will make them to melt. Now, they must have good electrical conductivity, that is another requirement, because if poor electrical conductivity means very high resistance, and as you pass very high current through that electrical heating, that resistive heating itself will produce so much of heat that will make the material to melt. So that is what we not want, actually we do not want, because we need to maintain the structural integrity of the device. Now, they must have good mechanical strength and machinability, because machinability is a very much important requirement, because you need to form your device, you need to design your device, and for that you need to machine the material in a way that your design requires. And if it is not extending that machinability, then you cannot make any device out of that material. So, but at the same time it must have good mechanical strength, so that it allows you to maintain the structural integrity under highly thermal, highly stressed condition, both mechanically and thermally. That they operate under very high temperature, and as well as somewhere they may have to withstand very high pressure, because of the electromagnetic body force may not allow the plasma to come out freely. They can pose as a barrier, and then the pressure of the cylinder can be exerted fully on the material surface. So that time, if there is not sufficient mechanical strength, then it may lead to deformation and which will disturb the structural integrity. So, you require the good mechanical strength and machinability. Then cooling for these electrodes are very much necessary because you are dumping so much of heat load and you need to take away the heat for structural integrity to be maintained. Then erosion resistance is another critical condition, consideration, especially for the thermochemical cathodes, because the reactions may corrode the device, corrode the electrode, and if corrosion continues, and then anyway the structural integrity hampers. And there is another thing, that arc constriction occurs over the cathode as well as the anode surfaces, and when such constriction occurs, huge amount of current density is occurs because of the very tiny cross section of the joining point. So, through a very small area of cross section, huge current passes through, and that generates a large amount of heat over a very small zone and makes the material to melt. So, that is the way it pits over the, it pits over the electrode surfaces, and such pitting causes the erosions, and over a long time the complete electrode get eroded, and once it get eroded, the eroded structure itself allows you to concentrate the electric field lines over the sharp zones, and that allows further erosion of the material. So, this is another feature which needs to be looked at, and they are usually much less when you are using a tungsten electrode and an inert gas environment, but they are usually very high when you are using some thermochemical cathodes and operating such devices. Now, these are the arc characteristics and the devices. You know that arc shows a negative VI characteristics, and they are having the regular features of very high current density, strong electromagnetic force, because the moment you are having high current density, the magnetic field produced is also high, and J cross B gives a radially inward force. So, that is a strong electromagnetic force it can pose. Then they are usually narrow because of the constriction, and when it gets constricted and you are passing a very high current, naturally the temperature goes high. Now, such devices are in two forms, as we have read in the class. I just summarize here, that is, they are transferred, in which the arc is connected to the job, and non-transparent when the arc is connected to the anode only, not connected to the job. So, these are the two different modes of connection of arc. Now, I come to a very interesting problem here about the plasma parameters that occurs again in most common plasmas that we are encountering every day. So, one is I have used solar corona. So, that is, you wake up with every day. Now, ionosphere, the space above the our atmosphere, and tokamak plasma, the fusion, the talk of the town, and glow discharge we are often encountering in your laboratory, and arc plasma, the processing plasmas, very regularly used in various industries. So, these are the 5 different types of plasma I have noted here, and for each of them I have noted the number density that may arise over there, and the kind of temperature we are expecting over there. And for those, we are now estimating in this problem 3 different parameters. One is your Debye length, one is your plasma oscillation frequency, another is the number of particles within the device sphere. So, this is just to make you familiar with the plasma parameters occurring in frequently encountered plasma systems in different areas. As I have told you, solar corona, ionosphere, tokamak, glow discharge, arc plasma, they are very common in application. Now, the quantities we are interested in, I have written the expressions. This is the Debye length, this is the plasma oscillation frequency, and this is the number of particles within device sphere. Sometimes we denote it by NDS, sometimes by this Coulomb parameter lambda, this big one, and this is the expression for Debye length, epsilon kT by n square. You note the dependency on T and N, one is in the numerator, one is the denominator. Then plasma oscillation frequency has no dependency on temperature, but it depends on N. It is in the numerators and square root. Then the number density, number of particles within Debye sphere, it is simple formula. You take the sphere and multiply by the number density and you get the number of particles within the Debye sphere. So with these three expressions, we now tabulate the quantities for these 5 types of plasma: solar corona, ionosphere, tokamak, glow discharge and arc plasma. And this table actually helps you to look at a glance actually. That what are the different parameters. You just go through the number density and you will see the kind of variation you are getting over here. You see that solar corona is 10 to the 12 per meter cube, and in tokamak fusion reactor you are getting 10 to the 20 per meter cube, and glow discharge 10 to the 14, arc you are getting 10 to the 21, ionosphere is the least one, it is getting 10 to the 10 per meter cube. Temperature Kelvin, so solar corona it is 10 to the 6, ionosphere 10 to the 3, then tokamak 10 to the 8, glow discharge you are getting this thing, and arc plasma you are getting 10 to the 4. So these are electron temperatures that I am listing over here. Now for arc plasma, because it is is thermal plasma, so this is same as the electron temperature and ion temperature, they are all same. But when you go to low pressure, lower pressure, then they are not the same. Now lambda d, the expression, what is that? Epsilon kT by n square. You calculate that over here, and in meter what you are getting, you see that starting from your 10 to the minus 5 meter that you are filling in tokamak to, it is going up to 0.02 meter, the longest one in case of your ionosphere. So the arc plasma is having 1.05 10 to the minus 5. So the least one you are seeing over here in the arcs, and the largest one you are seeing at the ionosphere. And this glow discharge and tokamak and this solar corona, you can just note down the figures of this Debye length. So this is 10 to the minus 3 meters, so it is of the order of millimeter. This is glow discharge, again 0.4 millimeter, but in case of tokamak it is 0.07 millimeter. So that is the kind of smallness or largeness that you can experience about the Debye length within which the plasma is able to shield. So this gives a very clear idea about that. So what is basically the purpose of this tutorial? And the plasma oscillation frequency. Omega is equal to 2 pi f. So that is, f is the linear frequency. So you can convert it, just omega by 2 pi is f, the linear frequency. So more or less linear frequency, the order will be the same. Okay. Now you see that the maximum one you are getting in arcs. So it is 10 to the 12, and the minimum one you are getting in the ionosphere. Then finally the number of particles within the Debye sphere, this is the one. You are seeing the least one is there in the arc, because the ionization is very less in arc plasma. It may be 0.1%, sometimes 0.01% kind of thing. So that is why because of the ionization is quite less, so number of particles in the Debye sphere naturally becomes less. And this plasma oscillation frequency, so when you disturb the plasma, how fast it oscillates to in an effort to equilibrate. So you see that frequency is very high in arc. It's quickly try to equilibrate, it is that oscillation frequency is very high, whereas in ionosphere it oscillates, and the oscillation frequency is quite low. It is in the order of 10 to the 7. So this tutorial basically allows you to have an idea about the plasma parameters that you encounter in most common plasmas, widely discussed, most commonly occurring plasmas, in a single place. So once these all are tabulated at one place, you can you freeze your idea about what kind of density that may happen in what kind of plasma, what may be the temperature there, what may be the kind of Debye length you are expecting, what may be the plasma oscillation frequency, and what may be the number of particles within the Debye sphere. These are all typical values, they are not the exact values, it will depend on the kind of operating condition that you have reached there, but typical values of these parameters you can get from this slide. So with this I stop here. I hope that you have enjoyed this tutorial. We will see you in the next tutorial in the next week. So thank you.